Good day to you from Anagalactic. We are currently in a series to produce a formal paper, as I'll highlight here. And that's not what we're going to talk about, but I thought you should know what you're in for. This particular video is part of a series to promote a book as well as the formal paper. And the formal paper does not have a title yet, but will probably be called Spheric Geometry. Spheric Geometry is just dry enough to, I think, pass muster as a good title for a formal paper, and indeed that will be the topic, although it kind of branches into numbers right away and then arithmetic and then a few interesting applications. Synthetic Idealism will be the title of my book. Books can be of any length, so we'll just leave it at that. It could be a very short book, but it will be in book form using LaTeX layout. Just a traditional book, but simply as a PDF, so you yourself will be able to comment into the book, and if you wish you could have your name attached, but you will become part of that book, which is about what? An extension of Bernardo Kastrup's amazing new framework for physics, which we will be talking about today, but in a certain application, which is hard to come by in the realm of consciousness, talking about that. But we'll just proceed right through here. We've covered this as a documentary on synthetic idealism and spheric geometry. Today we'll be talking about consciousness with a goal to see if we can broach the question of reality. That does seem to me to go part and parcel with the topic of consciousness. Give me a nanosecond here to expand this. All right, we've reordered our list and dropped a few items which were mostly meant to bracket what's happening right now, which is actually quite a bit. Reality is at the top of the list because that is our avowed goal today, according to the way I have this presentation laid out. We should be able to introduce the idea of reality, which I argue is unavoidable when speaking of consciousness. Now, there would be a reason for my statement. You see, I have an indented item, which is an adjective. Physical consciousness. Is consciousness physical? Well, you could certainly make a case for that. If you're using analysis, that is exactly how you would treat it. You want the facts, ma'am, just the facts. Where does consciousness occur? In the brain. Time to study the neurons and the structure of the brain. And there is a good deal of research going on in that direction. Now, to expand this list, we have non-physical consciousness. That's where we'll begin today. And then we go into non-physicality, which is a concept, and then a few names. And then we'll talk about what I want to talk about, which is non-physical space, and the discovery that I made recently within the past 5 years of a new space, which is saying something. That may sound profound. Well, that's why I have a lot of bracketing information at the beginning of my video presentations, so you'll know what you're in for. This goes very deep, very quickly, but I try to avoid the usual pitfalls of technicality, except where absolutely necessary, and I can guarantee you one thing I've learned in making these productions over the past 4.5 years is that is quite an art. I have great respect. I like to believe that I've always had great respect for the methodology of scientific communication. It is genuinely an art. I say that from the bottom of my heart, not meaning to be rhyme poetical. But here in our list, we are intending to get a definition of consciousness. Why? Why do we want to do that? Well, my goal is to express just what understanding something would mean if you could understand it. What kind of power would that imply? What kind of advantage would you gain from knowing anything about consciousness? Perhaps you already know it. Perhaps you know everything there is to know about consciousness. And how in the world would you find out anything more about consciousness than you already know from the fact that you are conscious? Well, it turns out that it's one of those subjects that if you describe it the way I just purposely did, it sounds dry and boring and really remote and kind of shady and probably won't get anywhere. That is exactly what I think is a normal that would be on my list if I knew nothing else about this topic. And so I invite you to consider with me the nature of consciousness from the point of view of why would you care? What possible good could come of knowing something more about consciousness? Well, in order to answer that question, and I'm the one who raised it, so this is rhetorical, you would want to have some kind of framework where you could establish goals, because what you're doing is you're setting up a goal. Well, why are you doing that? Do you have some pressing problem that needs to be solved? I just throw that out at the outset. I know that's kind of like baiting for some kind of philosophy discussion, but really at the very top of science, you'll find philosophy. It should not be convolute. Science is actually rather rigorous, and I prefer to stay on the side of rigor wherever possible because it's safer. Not that there's not pitfalls in itself with being too rigorous. Obviously, there is a danger in being too rigorous because then, well, obviously one could discuss that ad infinitum. But we are after consciousness, and the reason is that we have some problem, and we're not going to say what it is, for the reason that I believe that it's multiple choice on what you might fill in for yourself, but I'm pretty sure it doesn't matter. In other words, I am going to state at the outset that to know about consciousness, and which is contextual, or know what about consciousness? Well, that's the question. What is it about consciousness that would make it something that you might want to know something about it? Well, I would just say offhand, not saying whether my answer is right or not, but one of my first answers would be control. To control my consciousness. I actually don't recommend that as the best first choice, but it is a typical first choice in the way I kind of laid this out in my mind, polling myself as if I were a typical human. What would I say about consciousness? Would I be excited? Well, then the question would be, why are you excited about consciousness? Well, it could be because you want to control it. But I really don't believe that that's the right answer. But I'm not sure there is a right answer. You see what I'm saying here? Well, perhaps that's your goal. And who am I to say that controlling your consciousness, you yourself controlling your consciousness, it was my first choice. I mean, I can't really put it down, but I don't think that's the right answer. But then what is, if it's not to control your consciousness? Well, you see, I'm not sure what the answer to that is, but I know that there has to be some answer. And so if I were to give you an example, obviously it would be my own, which I'm not sure is the best example. In other words, I'm trying not to be prejudiced. I don't want to share some bias with you. Here's what I think is a good example of that. Well, I think I can't avoid it now because I haven't really given you much to go on. The question is, what's so great about consciousness that you just tell me something? Why the hell would I care? Well, because I'll show you. Actually, that's the reason why I want to give this video, is to answer that question, which I think you would have to admit is kind of makes you think. Makes you, stop and wonder because you haven't gotten anywhere yet. Well, that's one of the problems of induction, is that if you can just suddenly just see the answer, you just see it, well, you might have a difficult time expressing what it is, because how in the world did you figure it out? You would have to convince somebody of how you figured it out. How the hell did you see that? Otherwise, they're not going to listen. Oh yeah, the planets fly in ellipses. Sure, because you say so. Well, you're Johannes Kepler. You might be depressed to hear that. Because planets, in fact, do fly in ellipses, as he, in fact, discovered. So, there is a communicative effort going on here, and I'm trying to tell you what it is I'm about to try to tell you, which is that the reason why men, you have to do some research. That I just did that research. Is what do men say about that? It was a typical answer to that question. Well, it's quite a search to answer an abstract question like that. Like, what the hell good is consciousness? Well, the AI bot, as I found out, will indeed just treat that as an ordinary question. You don't want to use the F word, though. It just won't print it. Anyway. So, consciousness is the ultimate context because it's not a thing. But according to a certain way of thinking, which I happen to share, and I think you do too, you think of consciousness as something. It's just not a thing something. Well, we call that an abstraction. There are other fancy-dancy words which are not exactly the same because you don't know exactly what you're talking about. So you give it this word, you give what this word? Well, it's this process or just this ongoing awareness, and you start using these restricting words. Oh, awareness. Yeah, well, conscious would be aware. Aware of what? Well, your memories. This is what Krishnamurti was just talking about. Well, I just listened. This was actually decades ago. Krishnamurti and David Bohm were talking. They were talking about this, and Krishnamurti addressed just this question. Well, what is consciousness? Because David Bohm, being who he is, could ask some pretty intelligent questions of the great Krishnamurti. And boy, they got along well for 10 years. Made numerous interviews. They collaborated. They enjoyed each other's company. But boy, I'll tell you what, you got to really like philosophy and science to listen to those two cats talk, because it's not that it puts you to sleep, it's that it mesmerizes you. And in certain places, I mean, I'm not ashamed to admit this, I had to really concentrate because they go off on these paths and they know where they are, but you may have a tough time keeping up. And really, it's quite a journey, but the long and short of it was that consciousness is basically a whole bunch of things. It's like a house. It's like this house full of things. And so when you say, what is consciousness? It's like, well, open up the attic, open up the door to that room. Here's a closet. Here's the furnace room. It's like there's backyard, side yard. Here's the driveway, Here's the tree swing. There's all this stuff in the realm of consciousness. Like you say, memories. Well, yeah, that's always there. Carl Jung basically proved that in some dynamic sense. That's why his name is on this list. So speaking of this list, let's go through this. Consciousness can be considered something physical because it can be localized in the brain. I think that's about the fairest way of saying it. There certainly is a lot of research in that direction. How the neurons fire, which part of the brain communicates with the other parts. A lot of this can be measured. So there's a lot of anytime you can take measurements, physically oriented scientists, as we all must be in some way, definitely want those measurements, and so you tend to see what you're measuring. And that's physical. But consciousness, you would at least have to admit, for the sake of argument, if no other reason, that you could easily make the case that consciousness is a non-physical. But then you see, you do have to ask the immediate question, what do you mean by non-physical? Isn't anything that you can name physical? Gravity, I would say, is physical. So what is it about consciousness that makes it non-physical? That is an extremely deep question, it turns out, and it is not a wild goose chase to answer that question. That's what I'll be showing you today. That is the key question. Is what makes you posit a non-physical realm? Are you saying that it's imaginary? Because I do. But you see, I have a certain twist on all these words. Everything we're going to be talking about is physical. However, it entails a new definition of what do you mean when you say physical. And that's where we get to David Bohm, who kind of cracked the shell. He's kind of like the chick coming out of the shell. This is a new world being born. And Bohm was one of the first to get a view of the outside world. He's one of the first. He ended up going outside of science, which is indeed why he was talking with Krishnamurti, whose very name, if you know anything about Krishnamurti, this is no ordinary man by anybody's definitional basis. Krishnamurti is one of the most amazing men, just as a man, living on the surface of this earth. I just got some objective facts about this man, and I think the world of Krishnamurti. And his collaboration with David Bohm is absolutely precious. But as I said, you do have to be in the mood for it. You know, maybe spend a week reading Sherlock Holmes first, just to get ready for these two guys, because they're going to get to the bottom of things, and boy, they do. Krishnamurti is quite a gifted man, and David Bohm, in collaboration with Krishnamurti, is the man who can continue asking Krishnamurti relevant questions. And that's what you want, and Krishnamurti just eats it up. Because he wants to be able to express himself, but nobody ever asks him any great questions. And he gets so bored, it's obvious. I've seen him give lectures, and they're vastly interested in him, and there's a good reason they are. But I'll be honest with you, if you didn't know much about Krishnamurti, you would think that he was bored talking to these people. But when he's talking with David Bohm, he is not bored at all. He's animated, and man, is he cool to listen to. But he is being asked questions by a quantum mechanist scientist of the very highest order. Probably the greatest quantum mechanist of all time, because David Bohm was the only man who derived any kind of a rational statement about the system of quantum mechanics. Nobody else was able to say anything rational about it. But David Bohm found a way to say something rational about the system, which I find remarkable, if only for the reason that he's the only man who's ever accomplished that. Because everybody would like to say something profound about quantum mechanics. But David actually said something scientifically profound and made it stick. I believe that he was right. He calls it the implicate order. And from a purely mathematical mind, we're talking about a level of geometric insight, which is exactly what I look for in a scientist, because that's what gives you the greatest insights, is geometric insight. And he was onto it. The next name down, Bernardo Kastrup, that man has an immense following. He's incredibly liked, and I believe for excellent reasons. He developed a system called analytic idealism, which simply means that the correct framework for physics may have been nailed down a little too quickly without review, that the axiomatic basis of physics would clearly be physical matter. Bernardo Kastrup really basing his insight, I am sure, well, explicitly he says so, on quantum mechanics, where certain presuppositions on how you do things in science breaks down. In other words, science fails. So quantum mechanics, what it is connoting is a failure of science at a fundamental level. Is that we literally can't describe what we're seeing, because it makes no sense what we say. And no matter what we say, it continues to not make sense. And so now we're stuck with that. But it's interesting because it breaks into two halves. It's it's such a fascinating and poignant paradox, which can be stated in many ways. The quantum paradox is quite an abstraction because I can think of, and I used to try to list the examples, and at one time I thought I had as many as a dozen examples, but I'd say it wouldn't be too difficult to name 6 examples of the quantum paradox, one of which, of course, is entanglement, but probably the most deservedly famous one is Paul Dirac's immortal collapse of the wave function. He says that's the problem that needs to be solved, is that one, is the collapse of the wave function, because that's what doesn't make sense. That's actually, I'm not saying that I'm adding that, but I'm not sure I'm the first man to have said that. I mean, that's kind of begging the question. Oh, our lab cat is entering the house. I leave the door ajar. Oh yes, when is a door not a door? When it's ajar. That's a Bennett Cerf joke. 1,000 Bennett Cerf jokes. I tried to read it. It's the most boring book I ever read in my life. It was Bennett Cerf's jokes. Well, when your idea of a joke is, when is a door not a door? When it's ajar? Well, an 8-year-old doesn't actually understand that. So I always remember that. So now, so what we want to talk about is non-physical space, because of what Kastrup discovered, and because of what I discovered, which is what? Do we see space? Well, the answer is no, we don't see space, but do we detect space? You might say indirectly we detect space because it's not there. Is it not there? It is there. Space is there. The reason you can say that is because light travels through it. So it is a medium. It's a medium because it transmits light. Light can be transmitted through a photo-optic cable, an optical fiber cable. So it's traveling through a medium. Well, when it's traveling through space, it is also traveling through a medium, otherwise it couldn't travel. The definition of travel is to go through a medium. That's what travel is. So does light travel through a medium? Yes, it does. Well, then is space a medium? Yes, it is. So now you know what space is. Is it real? Yes, it's a medium. Is it ether? No, although that's a very strange word. The reason the word ether was adopted is because light travels through a medium. And so the medium was called ether, but it was given a characteristic that it must be elastic. It must be elastic. For instance, water has to be elastic to carry a wave. Well, the same is true of air. But light is different unless space is a medium. And that's what the word medium means. It behaves as an elastic material for the passage of a wave. And that was called ether. And since it was considered to be substantial, and who would not think so, since it can vibrate, it's like water or air. Well, those are real. So space is real. In what sense? That it's like air or water. So that's ether. But that was disproved. But it was disproved on the basis of a presupposition of what is matter. And so, actually, the case is still open. Well, what I discovered is the elasticity of space. And that's the first time I ever used that phrase. So this has been a very good video for me thus far. I never actually said that out loud. But that is what I discovered, because this new geometry predicates an elasticity to space. And this was first discovered by Ruđer Josip Bošković back in about 1745, is when he first had the idea. And he published just 18 years later in 1763. And then there was another edition of a book which is now considered to be immortal by those who know what's in it. Better than anything by Tesla. Better than anything you've ever heard of in any semi-science fiction novel is the work of Roger Boschkovich, and yet all it is the philosophy of science. There is mathematics to support his work. He was an extraordinarily top-notch mathematician. But his book has almost no mathematics in it at all, which may be the last book of that level that had virtually no mathematics, because it was geometric. And that's what I specialize in, is in non-physical geometry. Non-physical geometry, and that's the first time I ever used that term. So this is a really, really good video for me thus far, and I will continue, but I'm kind of enjoying myself. I'm just taking a little pause to... So to go on with this list, you'll see it says non-physical space, and I'm just going to scroll up a little bit further. Surface is a critical word, which I'll be talking about today, and the surface data type. Now, surface, again, when you have something like a lake, there's a surface to the lake. It's the interface between the water and the air is called the surface. Well, that's a geometric term as well. Can a line be said to have a surface? The correct and short answer is no. A line does not have a surface, but you may not know the exact reason for why that's true. In other words, someone might object and go, well, why doesn't a line have a surface? I see two of them. Because that's not a surface. So this gets into the definition of a surface, which becomes apparent when you draw a circle. Because a circle does have a surface, and that's what a surface is in its simplest form. It's a circle. And a circle connotes a very special kind of line. And it actually connotes two very special kinds of line. And we're switching from one space to two space. And that's the difference between a straight line and a circle. That a straight line only has one, and now I'm going to use an overworked word in a new way, but this is actually what is said in physics and in mathematics, that a line has one dimension. And since that is, you'll just say axiomatically true, you're saying so. But it can be logically demonstrated that what you're saying has a coherence to it, that it's a good thing to say. That the line only has one dimension, which is essentially its distance. The distance between 2 points is what that line is good for. So that's adding a lot to the mix, but a line is said to have one dimension for that reason. But when you draw a circle, it's obviously a 2, not a 1. What do I mean? That's a very abstract statement I just made. I hope you caught that. That to the proportion that when you draw a straight line, you're indicating oneness of something. But then you certainly would want to compare that with something else. And you can't really compare it with what's less than oneness, because that would be zeroness. Well, that's the definition of a point. But that's getting a little ahead of ourselves. What I'm trying to say is that the line has this oneness to the proportion that a circle has two-ness. What's the oneness and what's the two-ness? The oneness is a bipolar direction. That's a line. It's going in two bipolar directions. In other words, one part of it goes this way, and the other, the reflection as it's called, the reflection goes this way. So it goes in two directions. But actually that's just one direction with a valence. What it is distance, and it should all be positive. But if you take the reflection, you have the negative integers. And the central number is 0, otherwise you have no metric. So you've posited the very special number 0 when you draw a straight line. When you draw a circle, you do no such thing, and it does not have a oneness characteristic. When you draw a circle, you make a surface. And in 2D, this is called a 2D surface because of that straight line and the fact that there's another peculiarly oriented straight line on a plane such that they're perpendicular, called orthogonality. So that's why we say that the plane is 2D, is because you can compose it on two straight lines, called the metricization of the space, in this case planar space. So what you should learn from that is that you need one number to make one aspect of the plane, but you need two numbers to make both aspects of the plane, which is vertical and horizontal. Horizontal would be x, and vertical would be y, and that is the Cartesian coordinate grid system for the plane, from which we get a lot of our exercises in school, for instance, the Pythagorean theorem. So that's planar space that's been linearly parameterized, that is, it's been metricized on two linear numbers. So a linear number is a number that occurs on a line, but when you draw a circle, you're drawing a conjugate number. It's a conjugation of the vertical and horizontal. What is the word conjugation? It means that it's a two-component number instead of a one-component number. So that when you have the x-axis, all you have is a line, all you have are numbers, but they're one-component numbers. When you draw a circle, you're drawing a number. You're drawing a number that's composed of two numbers. The vertical aspect is one of those two numbers, and the horizontal aspect is the other of those two numbers. If you superimpose the grid again, you can compose what's called polar coordinates, where instead of taking the x measurement and the y measurement and doing interpolation, which is what you do with the Pythagorean theorem, you try to get a diagonal. That is a line that's not, you try to get a distance to a point on the plane, but you need two numbers to denote that point. So you're doing a combination of the x and the y components of that position, so that if you draw the position of that point at 2, 2, that's not the distance. The distance is on the diagonal, and that's when you use the Pythagorean theorem in order to get the distance to the point instead of its position. Its position is denoted as 2, 2. If it's at the x equals 2, y equals 2 point, its designation is a two-component composite number, where the definition of the relationship between x and y is the comma. So the position is x and y, but the comma denotes a relationship between the two, that is its distance. And you simply take the squares of those two numbers, add them together, and then take the inverse square, and you will find out that the distance from the origin to the 2, 2 point will be the square root of 8. In other words, it's about 2, well, it's exactly 2 times the square root of 2, which is not an exact number. It's a quite disturbing number called an irrational number, and the square root of 2 is one of the simplest, or one of the earliest, of the naturally occurring irrational numbers, which are a problem. Yes, because you're not getting an exact answer. You actually can't, and that's actually profound, that you cannot get an exact answer for what is the distance on a plane. Because of the square root function, it ruins everything. At a certain, you have to admit that. it's highly debated how much difference that could possibly make. And the argument has been going on for centuries, so we don't need to actually argue it here. But it is worthwhile pointing out that irrational numbers are simply problematical. That is certainly fair to say. It's just a question of how political you get about it. Like, is this harming our children to teach them irrational numbers? Oh my God, you know? Well, the answer is yes and no, as most answers are these days in high-level physics. And that's the Schrödinger cat problem. The answer is yes and no at the same time. It's not that alive and dead. That he did that as a parody. The real paradox is yes and no at the same time. It's true and false at the same time. It's that you can't have it both ways at the same time. You're getting it both ways, but you can see that you can't have it both ways, so how come you're getting it both ways? Well, you can lose your mind thinking about that. It's almost requisite at this point. You would have to say, whatever is the solution to that, you would probably have to go stark staring mad to see it. Well, I found out that quite the contrary. Oh, this is science at its best. So what's the answer that I've come up with? Well, it's that you've noticed that imaginary space keeps coming up. Einstein used imaginary space in his formulation of space-time, and it's called that. And it is imaginary. A fourth orthogonal axis? A fourth orthogonal axis. That's imaginary. Well, we use imaginary numbers all the time in the complex numbers. They are imaginary. You see, this is part of my discovery. It turns out that imaginary space comes up over and over and over again. Is that you go into imaginary space really every time you hit an irrational number. Because it's imaginary with respect to computability. So it's a relatively imaginary realm. What I discovered is a new definition of space that redefines space as having an innate imaginary component. Which, looking back, I mean, just saying this out loud, that almost seems tautological. In other words, I've been able to define why you can't see space. It's because it's not there. And yet it is. So this is the ultimate physicality of the paradox, the Schrödinger cat paradox, the true and false at the same time. Well, if that's literally true of physical space, then we do not yet have an accurate definition of physical space. And so I've discovered geometrically where is the missing space. The invisible part of space. We can see space because light travels through it. That defines the visibility of space. You must be able to see space, or light would not be able to get from where it had been to your eyes. It had to go through space. Well, then it's something. It didn't go through nothing. It went through something. But you see, that doesn't fully describe space, and that's why we're so baffled in trying to describe, for instance, the curvature of space. That curvature of space, which is space-time curvature, it's called that. That's an artificially applied curvature. There is a natural curvature to space when it's seen in a certain way. But it's incorrect to say that space is curved unless you can prove it. You've got to prove that the space itself is curved if you're going to say curved space-time. Because you see, time in this construction is not different from space. You see, it is space. That space is time. Well, what I discovered is that the reason Einstein was able to discover that is because the relationship between time and space is consistent across two number systems. Which is a remarkable thing to say, because what do I mean by two number systems? Well, remember, the line has a one-component number system. I mean, that nobody argues that. But what is interesting to say is that the plane has a two-number system. It's x and y. But what if that were just one number, and you were able to use numbers to denote the parts of a circle? In other words, we have a line in Euclidean geometry, but it's useless without a metric. In other words, it has to be useful. Well, we use it for distance, and that requires a zero, or you don't have an initial starting point for the quantum jump to whatever your Planck length is. And that's introducing a lot of terms, but you may have understood what I just said, but let me explain it a little more carefully. When you try to set up points on a line, you have to start with the first point. And the problem with doing that is now you have a point, but you also have the distance from one point to the next. And that's Euclidean geometry axiomatically stated, that the shortest distance between 2 points is a straight line. So, but what that means when you go to draw it is, you can't have a line without having 2 points, right? But have you said enough? No, you left out something. You can't have a line without 2 points and nothing in between the 2 points. Nothing in between the 2 points. Well, this is where it gets down to angels on a pinhead. And there have been quite a few extremely powerful minds. And it goes on to this day. Is if you're going to measure distance on a line, you have to start with a quantum jump. And the quantum jump is the ultimate spooky fucking thing you can do. Because you have a line, but you need to measure a distance. Well, that means you need two things that really don't exist. One of them is a starting point that has no dimension. So it's a point of nothingness on an otherwise undefined line. But you're saying that the line is made of those points now. That's what you do. But you see, that's an overstatement, because you can't make a line out of points. Because if you could make a line out of points, it would all merge into one point. So there has to be a separation between the points. Well, what's that? Well, it's nothing. Well, then your very first distance is nothing. But that's not true. Your very first distance is the unit of your distance, because it's the shortest distance that you can draw on the line. That doesn't exist. There is no shortest distance you can draw on a line. If you draw a point, you cannot draw a point next to it. You can't make them touch unless they're circles. But if they're circles, then they have an interior, and that's called a surface. If an object has an interior, then it has a surface. The interesting question then comes up in analyzing the 4 basic lines, which is the zero curvature line, the hyperbolic line, the parabola, the elliptical line. Those are the 4 lines on a plane. The straight line has infinite eccentricity. The range of the family of hyperbolae have an eccentricity that is less than infinity, but greater than 1. The family of ellipses has an ellipticity that is less than 1, but greater than 0. So in the system of circles measured that way, there is no zero ellipticity. That means there's a quantum circle. That's a lot of information, and we've come up to 45 minutes. We just ended one of the hottest days of the year, and the house is still hot, so forgive me if I appear to be perspiring. I am. So we'll be back later, and we'll talk about how the surface of the quantum circle has such far-reaching consequences because the interior of that circle is imaginary space. The exterior of that circle is the space that light travels through, physical space. It's the ether. But the ether has a space called contra-ether. And I discovered that, and that's another new term. So I've been studying this for 4.5 years now, and I just make discoveries regularly. It's just now routine. So it's definitely the answer vector, and we're now going to approach the subject of consciousness to get an extremely useful answer of what it is. And you're going to be surprised. Stay tuned. Keep looking up. We have a waning half moon. I'm sorry. Yes, waning is less and less, right? All right, we'll be right back. And thank you for tuning in to Anagalactic.